There's a picture of the solar system that almost everyone carries in memory, even if they have not seen it for years. The sun sits on one side like a bright coin. The planets trail away from it in a tidy line. Mercury, Venus, Earth, Mars, a little gap, Jupiter, Saturn, Uranus, Neptune. Sometimes Pluto is still there, sometimes not. And beyond the last planet, if the artist remembered to include it at all, there is a narrow, dusty ring with a small label, Kuiper Belt. That picture is not exactly false. The order is right. The names are right. Neptune really does orbit far beyond Uranus. Pluto really does belong to a population of icy bodies beyond Neptune. But the picture commits a deeper error. It teaches your mind to believe that the solar system is mainly the planets, and that everything beyond them is a thin decorative border, a frozen trim at the edge of the drawing. The real solar system is not shaped like that picture. It is not a compact family of planets surrounded by a modest belt. It is a small, bright core, buried inside a huge, dark architecture. The part you learned first, the region of familiar worlds, is only the inner chamber. Past Neptune, the sun still holds thousands of objects in slow, cold orbits. And the first great frontier of that darkness is the Kuiper Belt. The question is not simply how big the Kuiper Belt is. Numbers alone are not enough. The deeper question is why this region, drawn as a thin line on a classroom poster, changes the story of the entire solar system. Is it just a belt of leftover ice, or is it a fossil record of a violent migration, a frozen archive of planet formation, and a warning that the neat map we inherited was never the true shape of our home? To answer that, we have to begin by destroying the scale in your head. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers, about 93 million miles. Light needs a little more than 8 minutes to cross it. That already sounds large, but we live close enough to the Sun that 1 astronomical unit has become a convenient measure, almost a friendly one. It is the ruler astronomers use when ordinary kilometers stop behaving like ordinary numbers. Earth orbits at 1 astronomical unit. Mars moves around 1.5. Jupiter is a little more than 5. Saturn is around 9.5. Uranus is about 19. Neptune, the last major planet, circles the Sun at about 30 astronomical units. By the time you reach Neptune, sunlight has faded to a pale, remote version of itself. The Sun is no longer a great disk in the sky. It is a brilliant point, still powerful, still dominant, but emotionally changed. The warmth that rules Earth has become a memory written in light. 30 astronomical units feels like the end because our maps tell us it is the end. The old solar system, the schoolbook solar system, has trained us to treat Neptune as a final gate. After Neptune, the diagram seems to say, the scenery stops. A few small icy bodies remain, and then the page runs out. But the Kuiper Belt begins near Neptune and extends through the region where many icy bodies orbit between roughly 30 and 50 astronomical units from the Sun. The exact boundaries depend on which population you are describing. The classical belt is not the same thing as the scattered disk, and the outer solar system refuses to behave like a clean engineering diagram. But as a working picture, 30 to 50 astronomical units is the crucial first correction. It means that the main belt is not a narrow rim. It is a wide shell of space whose radial span is about 20 astronomical units. 20 astronomical units is not a caption. It is about 3 billion kilometers. It is about 2/3 of the Sun to Neptune distance. It is larger than the distance from the Sun to Uranus. It is larger than the gap between most of the planets that fill the imagination of the inner solar system. If you draw the Sun to Neptune distance as a long road, the Kuiper Belt adds another road beyond it, almost as long as the first, and that is only the beginning. A spacecraft moving through this region is not crossing a decorative line. It is crossing years of distance. New Horizons took nearly a decade to reach Pluto, which orbits within this outer realm. After Pluto, it still needed years to reach Arrokoth, a much smaller Kuiper Belt object farther along its path. Even after those flybys, the spacecraft did not suddenly emerge from some clean edge into a different universe. It continued outward through the same deep architecture, sending back data from a region so wide that the human word belt almost becomes misleading. A belt sounds like something tight, something you can hold, something with a clear edge. The Kuiper Belt is better imagined as a vast, dim, uneven wilderness of frozen bodies spread through billions of kilometers of darkness, so thinly populated that a spacecraft could pass through it without ever seeing anything unless it was aimed at a target with exquisite precision. That emptiness is the second shock. When people hear the word belt, they often imagine crowding. They imagine the asteroid fields of films, tumbling rocks everywhere, a place where navigation means dodging debris. But real belts in space are not like that. The asteroid belt is mostly empty. The Kuiper Belt is emptier still. Astronomers estimate that it contains enormous numbers of icy bodies, including hundreds of thousands, larger than about 100 kilometers across, and many more smaller objects. But those objects are scattered through such an immense volume that the average separation between meaningful neighbors can be measured in millions or tens of millions of kilometers. A world can be part of a belt and still be almost alone. Imagine a museum the size of a continent, and inside it only a few thousand artifacts, each locked in a cold room so far from the next that walking between them would take years. That is closer to the truth than the cinematic asteroid field. The Kuiper Belt is not dangerous because it is crowded. It is difficult because it is vast. It hides objects not behind other objects, but inside distance itself. This is why discovering Kuiper Belt objects took so long. Pluto was found in 1930, but for decades it seemed like an odd outlier rather than the visible member of a larger population. Astronomers suspected a broader belt of icy bodies might exist beyond Neptune, but suspicion is not detection. These objects are small, distant, and dark. They receive little sunlight, reflect only a little of what they receive, and crawl so slowly across the background stars that finding them requires patience, precision, and a willingness to search for moving specks that barely announce themselves. The first confirmed Kuiper Belt object beyond Pluto and Charon was found in 1992. That date matters. It means the outer architecture of our own solar system, not of a distant galaxy, but of our home, became observationally real only within living memory. For thousands of years, humans looked up and mapped the bright planets. For centuries, telescopes improved. For generations, the solar system seemed nearly complete. And then, at the end of the 20th century, a new region appeared, not because it had been absent, but because our instruments and our patience finally reached it. The solar system became larger not in space, but in human understanding. The first lesson of the Kuiper Belt is scale. The second is emptiness. The third is age. Most Kuiper Belt objects are not worlds that have been reshaped over and over like Earth. They are cold relics. Their material comes from the early solar nebula, the disk of gas and dust that surrounded the young sun about 4.6 billion years ago, Close to the Sun, heat allowed only rock and metal to condense as solids, so the inner planets became rocky. Farther out, beyond the frost lines of different volatile compounds, water, methane, nitrogen, carbon monoxide, ammonia, and other substances could freeze. The outer solar system became a place where chemistry hardened into ice. This matters because the Kuiper Belt preserves material that never became a major planet. It is not just a junkyard. Junk is what remains after usefulness has passed. The Kuiper Belt is more like an archive. It contains material from the construction site of the planets, fragments that avoided being swallowed by a growing world, fragments that survived the gravitational reshuffling of the giant planets, fragments that still carry clues to the earliest conditions around the Sun. A small icy body there may look insignificant, but its orbit, color, shape, and composition are records. They tell us where it may have formed, how violently it was moved, whether it collided, whether its surface has been irradiated for billions of years, whether it was born as a pair, whether it belongs to an ancient, undisturbed population or to a group thrown outward by Neptune. In the inner solar system, weather, geology, volcanism, impacts, oceans, and atmospheres erase and rewrite surfaces. In the Kuiper Belt, cold slows the eraser. Not everything there is unchanged. Pluto showed us that very clearly. But many small Kuiper Belt objects are among the best preserved witnesses we have. Pluto is the great exception that became the gateway. For much of the 20th century, Pluto was taught as the ninth planet, a small, strange world at the edge of the solar system. Its orbit was tilted, elongated, and partly inside Neptune's orbit. It did not fit comfortably with the giant planets, but as more objects were discovered beyond Neptune, the problem shifted. Pluto was no longer a lonely oddity. It was the largest familiar member of a family. That reclassification was emotionally difficult for many people, because planet is not only a technical word in culture, it is a childhood category. It sits in memory with classroom songs, painted models, and a sense of order. But science does not owe our childhood categories permanence. When a new population is discovered, language has to adjust. Pluto did not become less interesting when it became a dwarf planet. In some ways, it became more interesting. It stopped being the misfit last planet and became the first ambassador of an entire zone. Then New Horizons arrived. When the spacecraft flew past Pluto in July 2015, it did not find a simple dead ice ball. It found complexity, a thin atmosphere, haze layers, mountains made of water ice, hard as rock in Pluto's cold, vast plains of nitrogen ice, a heart-shaped region whose smoothness suggested geological youth, evidence that frozen materials can move, convect, flow, and refresh the surface, even in a realm where sunlight is weak and temperatures are unimaginably low. That was a powerful correction. Distance does not guarantee simplicity. Cold does not guarantee death. A world can be far from the sun and still have processes, structure, history, perhaps even an interior that has not fully gone quiet. But Pluto is not representative of every Kuiper Belt object. It is large enough to be round under its own gravity, large enough to hold volatile ices, large enough to have moons and an atmosphere, at least a thin and shifting one. To understand the smaller, more primordial side of the belt, New Horizons had to visit something else. In 2019, it flew past Arrokoth. Arrokoth is not a dramatic dwarf planet. It is a small, reddish, double-lobed body, about a few tens of kilometers long, shaped like two flattened pieces gently joined together. It looks less like a miniature planet than like a memory of how planets begin. Its two lobes appear to have come together slowly, not in a violent shattering collision, but in a gentle merger. That shape matters because it supports the idea that, in the early solar system, small bodies could form through the gradual concentration and soft assembly of pebbles and planetesimals, rather than only through destructive impacts. Arrokoth is quiet. Pluto is active. The difference between them is one of the richest lessons in the belt. The Kuiper Belt contains both worlds that have evolved and fragments that have remained close to primordial. It is not one kind of object. It is a population with layers of history. To read that history, astronomers do not only examine surfaces, they examine orbits. An orbit is a fossil made of motion. It is not a mark on stone, but it can last for billions of years. The tilt of an orbit, its shape, its distance from the Sun, its relationship to Neptune, all these features tell a story about the forces that shaped it. And when astronomers began to map Kuiper Belt orbits, they found that the belt was not a smooth ring. It has families. Some objects belong to the cold classical population. Cold here does not mean temperature. Everything out there is cold in the ordinary sense. In orbital dynamics, cold means calm. These objects have relatively circular orbits with low inclinations, staying close to the plane of the planets. Many are reddish. Many are binaries. They appear to have been less disturbed than other populations. They may preserve the local conditions of the outer solar system better than almost anything else we can study. Other objects are hot classicals. Their orbits are more tilted, more eccentric, more dynamically excited. They carry the marks of disturbance. Something stirred them. Something lifted them out of calmer paths. Then there are resonant objects locked in mathematical rhythms with Neptune. Pluto belongs to the most famous group, the Plutinos, which are in a 3-to-2 resonance with Neptune. For every 3 orbits Neptune makes around the Sun, Pluto makes 2. This rhythm protects Pluto. Even though Pluto's path crosses inside Neptune's distance from the Sun, the timing of the resonance keeps the two bodies far apart. It is not luck. It is orbital choreography. Other resonances exist: 2-to-1, 5-to-2, 7-to-4. Each resonance is a gravitational address, a place where Neptune's repeated tugs can trap objects into stable patterns over enormous spans of time. If the Kuiper Belt were music, these resonances would be deep notes, repeating slowly for billions of years, holding icy bodies in rhythms set by a planet too distant to see with the naked eye. Then there's the scattered disk, objects on elongated, often tilted orbits that can carry them far beyond the classical belt. These bodies are the aftermath of stronger gravitational encounters. They are the ones that Neptune kicked, disturbed, or displaced. Some dive inward near the region of Neptune and then travel outward to dozens or hundreds of astronomical units. They blur the line between the Kuiper Belt and the larger outer solar system. This structure points to one central mechanism. Neptune did not merely sit beside the Kuiper Belt. Neptune sculpted it. But the deeper surprise is that Neptune itself may not have always been where it is now. For a long time, it was tempting to imagine the solar system as a finished clock. The planets formed in their present orbits, the debris belts formed around them, and time simply aged the surfaces. That picture was elegant, but it could not explain the detailed architecture of the outer solar system. Models that place Neptune in its current orbit from the beginning struggled to reproduce the observed Kuiper Belt populations. Then researchers allowed the giant planets to migrate. The result changed the story. In leading models of early solar system evolution, the giant planets formed in a more compact arrangement. Interactions with a massive disk of leftover planetesimals caused Jupiter, Saturn, Uranus, and Neptune to shift their orbits. Neptune moved outward through a dense primordial field of icy bodies. As it migrated, its resonances swept across the disk, capturing some objects, exciting others, scattering many, and ejecting huge amounts of material from the solar system entirely. This means the Kuiper Belt we see today is not the original belt in full. It is the surviving remnant after a massive gravitational clearing. The current belt contains only a small fraction of the material that may once have occupied the outer solar system. The rest was scattered inward, outward, into resonances, into the Oort cloud, into interstellar space, or into collisions with planets and the sun. The Kuiper Belt is therefore not only a place, it is a ruin of a larger structure. That word should not make it feel dead. Ruins are valuable because they preserve the shape of what happened. Neptune's migration is written into the belt like a storm track preserved in sand. The quiet, cold classicals may be the protected floor that the storm did not fully erase. The resonant objects may be stones caught in the moving teeth of Neptune's gravity. The scattered disk may be the debris flung from the impact of a planet's outward march. The solar system was not born as the stable diagram on the wall. It passed through an era of rearrangement. Giant planets shifted. Small worlds were displaced. Populations were thinned. Orbits were lifted and stretched. The Kuiper Belt is the memory of that violence, preserved in slow motion at the edge of sunlight. This is why the belt's emptiness is not a sign of insignificance. It is part of the evidence. A belt that may once have held far more mass is now sparse, because the architecture changed. The emptiness is a scar. There is another way the diagram misleads us. It makes the belt flat. The planets orbit roughly in the same plane, the ecliptic, so diagrams draw the solar system as a flat arrangement. The Kuiper Belt is often placed in that same flat plane, like a narrow ring drawn with a compass. But real Kuiper Belt objects do not all stay near that plane. Many have tilted orbits. Some rise far above and below the ecliptic. The cold classical population remains relatively thin, but the hot classicals and scattered objects puff the outer solar system into a thick three-dimensional structure. A flat ring is easy to draw. A wide, lumpy, inclined, dynamically sculpted torus is harder. So the flat ring wins in public imagination. But if you could stand far outside the solar system and somehow make every icy body visible, the view would not resemble a neat bracelet around the planets. You would see the planets clustered close to the sun, almost huddled in the bright center. Around them would be a vast diffuse zone of small frozen bodies, brighter in some orbital families, thinner in others, tilted and puffed up in places, stretched outward by scattered orbits. It would look less like a ring and more like a frozen weather system, structured by gravity over billions of years. And if you looked beyond it, you would see that even the Kuiper Belt is not the final boundary. Past the classical belt, the scattered disk carries icy objects onto orbits reaching far beyond 50 astronomical units. Beyond that, objects like Sedna hint at another population. Sedna never comes close enough to Neptune for Neptune alone to explain its orbit easily. Its closest approach to the Sun is far beyond the main belt, and its farthest distance reaches hundreds of astronomical units. Its orbit is so elongated and remote that it seems to remember an event we did not witness. Maybe the young Sun formed in a cluster, surrounded by neighboring stars, and one of those stars passed close enough to tug distant bodies into strange orbits. Maybe an undiscovered planet shaped some of these paths. Maybe the early outer solar system had structures we have not yet reconstructed. Sedna does not solve the mystery by itself, but it proves that the region beyond the Kuiper Belt is not empty in the simple sense. It contains clues, and we have only found a few. Farther still is the Oort cloud, a hypothetical but strongly motivated reservoir of icy bodies surrounding the Sun at enormous distances. It has not been directly observed. That caution matters. We infer it largely from the behavior of long-period comets, which arrive from many directions, not only from the plane of the planets. A spherical source explains that pattern. The Oort cloud is thought to begin thousands of astronomical units from the Sun and extend perhaps to tens of thousands, or even around 100,000 astronomical units. At that scale, the solar system becomes almost interstellar. The Sun's gravity is weak, but not absent. Passing stars and the tidal field of the Milky Way can perturb distant cometary bodies, sending some inward after long dormancy. A comet that appears in Earth's sky may have spent millions of years in the outer dark before a tiny gravitational nudge changed its fate. This layered architecture is important. The planets are not the solar system. They are the inner visible rooms. The Kuiper Belt is the first vast outer archive. The scattered disk is the disturbed transition. Sedna-like objects are messengers from a poorly known middle distance. The Oort cloud, if our model is broadly right, is the nearly spherical outer memory of the Sun's formation environment and the giant planet's early scattering. The solar system is not a line. It is a nested set of dynamical histories. Yet the Kuiper Belt remains special because it is close enough to study directly. We cannot yet see individual Oort cloud bodies. We can barely sample the Sedna-like region. But the Kuiper Belt is within reach of powerful telescopes and, with great patience, spacecraft. It is the outer solar system's first readable book, and the pages are still mostly unopened. The objects we have cataloged are only a sample. Many are too faint, too small, too distant, or hidden in regions of sky not yet surveyed deeply enough. Observational bias matters. We tend to find objects where our telescopes look, at times when objects are bright enough, moving slowly enough, separated from the crowded background enough to be noticed. Any pattern in the known population must be treated with caution until we understand what our surveys might have missed. This caution is especially important when discussing Planet 9. Several very distant trans-Neptunian objects appear to have orbital alignments that some researchers argue are best explained by a large unseen planet far beyond Neptune. The proposed planet would be several times Earth's mass on a distant, elongated orbit. If it exists, it would be one of the most dramatic discoveries in solar system science since the first Kuiper Belt objects, but it has not been found. Alternative explanations remain possible. The apparent clustering may be partly due to selection effects. The sample is small. The outer sky is enormous. A real pattern and a biased pattern can look similar until the data set grows, so the correct scientific position is not to declare Planet 9 real, and not to dismiss the question as fantasy. The correct position is that the outer solar system still contains enough unknown structure for a planet-sized hypothesis to remain worth testing. That, by itself, is remarkable. In the 21st century, after spacecraft have visited every major planet, we still cannot say with certainty whether another large planet hides in the deep outskirts of the Sun's domain. The Kuiper Belt keeps teaching humility. It also connects our solar system to others. Around many stars, astronomers see debris disks, broad rings or belts of dust, and small bodies left over from planet formation. Some are shaped by planets we can detect. Some contain gaps, clumps, warps, or sharp edges that imply gravitational sculpting. The same basic story appears elsewhere. Planets form, leftover material remains, gravity organizes and disturbs it, and the debris becomes a record of the system's architecture. Our Kuiper Belt is therefore not just a local curiosity. It is the nearest example of a phenomenon that may be common around stars. It gives us a resolved, object-by-object view of processes that around other stars we can usually see only as blurred rings of infrared light or scattered dust. When we study the Kuiper Belt, we are not only studying Pluto's neighborhood, we are learning how planetary systems preserve their leftovers, how migration reshapes debris, how small, icy bodies store the chemistry of birth environments, and how the quiet outskirts of a star system can reveal the violence that made the inner order possible. That is the editorial center of this story. The Kuiper Belt matters not because it is crowded, not because it is close, not because it is easy to dramatize, but because it is the place where the solar system stops looking like a neat planetary machine and starts looking like an archaeological site. The claim is simple. The Kuiper Belt is a major structural component of the solar system. The mechanism is gravitational and historical. Icy planetesimals formed in the cold outer disk. Then Neptune's migration and resonances sculpted their orbits, scattering most material and preserving a remnant. The evidence comes from the belt's scale, its populations, its resonances, New Horizons flybys, and the distribution of distant objects. The limitation is equally important. Our census is incomplete. Our models of migration are still refined, and the most distant regions remain largely inferred rather than directly observed. The consequence is profound. The solar system is not finished at Neptune, and our understanding of it is still young. To feel how young, remember the timeline. Uranus was discovered in 1781, Neptune in 1846, Pluto in 1930. The first recognized Kuiper Belt object beyond Pluto in 1992. New Horizons reached Pluto in 2015 and Arrokoth in 2019. That means the detailed exploration of this enormous region is younger than many people alive today. We are not heirs to an ancient complete map. We are living during the map's first serious draft. The next draft will be sharper. Wide-field surveys, including the Vera C. Rubin Observatory's Legacy Survey of Space and Time, are designed to repeatedly scan large areas of the sky and detect faint moving objects. As such surveys expand the catalog of trans-Neptunian objects, orbital families that now look uncertain may become clear. Apparent clusters may dissolve as biases are corrected, or they may strengthen into evidence for new structure. The cold classical population may reveal more binaries and color patterns. The scattered disk may show connections to comet reservoirs. Distant objects may trace the boundary between Neptune's influence, early stellar encounters, and unknown outer architecture. The outer solar system is not waiting passively. It is moving slowly, but it is full of slow information. A Kuiper Belt object may take hundreds of years to orbit the Sun. Pluto's year lasts 248 Earth years. Eris takes more than 5 centuries. Sedna takes roughly 11,000 years. These timescales are not just trivia. They change what it means to observe. We cannot watch a full orbit of many distant bodies in a human lifetime. We infer the path from a small arc and refine it over time. The farther out an object is, the more patience the orbit demands. Astronomy becomes a collaboration between generations. That is why the Kuiper Belt is not only a place of distance, but a place of delayed understanding. Its objects move so slowly that certainty accumulates over decades. Its faintest members require repeated surveys. Its spacecraft missions take enough time to span careers. A Pluto orbiter if one is someday sent, would likely require a journey of many years, perhaps decades, before it could begin the work New Horizons only introduced. A mission to Eris, or another distant dwarf planet, would test institutional patience as much as engineering skill. The belt resists the human tempo. In the inner solar system, missions can move from concept to arrival within years. Mars can be reached in months, the Moon in days. The Kuiper Belt asks for something different: the willingness to send a machine into darkness and wait nearly a generation for the close-up. That waiting is part of the science. It forces a civilization to think beyond immediate reward. And when the machine arrives, the reward is not merely an image, it is a correction of imagination. Before New Horizons, Pluto was a dot and a set of measurements. After New Horizons, it became a world with landscapes. Before Arrokoth, small cold classical objects were points in orbital catalogs. After Arrokoth, one of them became a contact binary with a shape that spoke directly to formation mechanisms. This is what exploration does. It converts symbols into places, but it also shows how dangerous it is to assume that distance makes objects boring. Pluto was not boring. Arrokoth was not meaningless. The next Kuiper Belt object we visit will almost certainly be different from both. The outer solar system is not a warehouse of identical ice chunks. It is a population shaped by size, composition, collision history, radiation, rotation, binary formation, and orbital evolution. The cold classical belt may contain many binaries because gentle formation and low encounter speeds allowed pairs to survive. Some dwarf planets have moons. Haumea rotates so rapidly that it is stretched into an elongated shape and even has a ring. Makemake has a small moon. Eris is massive, remote, and bright enough to suggest a surface coated with frozen volatiles. Each object is a different experiment performed by the same early solar nebula under slightly different conditions. The belt is therefore not a single answer. It is a library of partial answers. What does it tell us about planet formation? That small bodies can assemble gently, that migration can scatter material violently, that resonances can preserve order inside chaos, that volatile ices survive in the deep cold, that large dwarf planets can remain geologically or atmospherically interesting far from the sun, that our solar system lost most of the original outer disk, leaving behind a sparse remnant rather than a complete record. What does it not yet tell us? The exact route of Neptune's migration, the full mass of the original planetesimal disk, the true number of small bodies, the extent of distant populations, whether an unseen planet exists, how common Pluto-like complexity is among dwarf planets, how sharply the classical belt transitions into other populations. These are not failures. They are the frontier. Good science is built not only on claims, but on boundaries around claims. So we should be careful. The Kuiper Belt does not prove every detail of the Nice model. It supports the broad need for giant planet migration, but competing versions remain. Arrokoth does not prove that all planetesimals formed exactly the same way. It provides strong evidence for gentle accretion in at least part of the cold classical population. Pluto's activity does not mean every dwarf planet in the belt is active. It shows that small cold worlds can be more complex than expected. Planet 9 is not a discovery. It is a hypothesis motivated by debated patterns. The Oort cloud is not an observed shell of photographed objects. It is an inferred reservoir supported by comet dynamics. The mystery becomes stronger, not weaker when stated honestly. Because the honest version leaves us with a more interesting universe. Not a universe where every dramatic claim is already proved, but one where a familiar map keeps opening hidden rooms. The Kuiper Belt's most unsettling lesson may be that we confused familiarity with knowledge. We knew the name Pluto, so we thought we knew the edge. We memorized the order of the planets, so we thought we understood the system. We saw the diagram, so we thought we had seen the architecture. But the diagram was a teaching tool, not a faithful portrait. It helped us learn the order while quietly erasing the emptiness, the width, the depth, the populations, the migration, the archive. Maps simplify. That is their purpose. The danger comes when simplification hardens into belief. If you compress the distance between planets enough to fit the page, you teach the eye that space is crowded. If you draw the Kuiper Belt as a thin ring, you teach the mind that it is minor. If you make the outer solar system flat, you erase the tilted orbits that hold its history. If you end the picture at Neptune, or just beyond Pluto, you erase the scattered disk, the Sedna region, and the possible Oort cloud beyond. A good map is honest about what it sacrifices. The old solar system poster rarely was, but this is not a reason to despise those diagrams. They are useful beginnings. A child needs a first picture. The problem is that many adults never receive the second picture. They carry the simplified map for the rest of their lives, unaware that it was never meant to survive contact with scale. The second picture is harder. It is mostly empty. It is not centered on drama. The sun becomes small not because it is weak, but because distance wins. The planets become a compact inner arrangement. Neptune becomes not an end, but a gate. Pluto becomes not a demoted disappointment, but a clue. The Kuiper Belt becomes a vast frontier of slow ice and older history. And the outer solar system becomes a lesson in humility. Consider sunlight there. At 40 astronomical units, sunlight is about 1,600 times weaker than at Earth. Noon on a Kuiper Belt object is not like noon here. The sun is a small, hard light in a black sky. It can still shape surfaces, still drive faint chemistry, still mark the direction of orbit and season, but it no longer dominates the senses as it does on Earth. A world there is not warmed by the sun in any familiar way. It is preserved by distance. That preservation is why color matters. Many Kuiper Belt objects appear reddish, likely because radiation processes simple ices and organic molecules into more complex materials called tholins. These surfaces are chemistry under cosmic exposure, slowly altered by ultraviolet light, charged particles, and time. Color becomes a clue to surface history, composition, and dynamical class. The red of a distant object is not decoration. It is a weathering record written in the outer dark. Shape matters too. A rapidly rotating body can stretch. A gentle merger can preserve a double-lobed form. A collision family can reveal a past impact. A moon can let astronomers calculate mass. A binary can preserve formation conditions. In a region where objects are often too distant to resolve in detail, every small piece of information becomes valuable. Even absence matters. A lack of craters on part of Pluto suggests resurfacing. A lack of detected small objects in some orbital ranges may indicate real structure or observational limits. A gap in a distribution may be Neptune's signature, or the shadow of survey bias. The outer solar system is full of silences that have to be interpreted carefully. This is why the Kuiper Belt is not only a subject for planetary science, it is a test of scientific patience. It asks us to separate what is seen from what is inferred, what is model-dependent from what is measured, what is probable from what is possible, and what is simply unknown. That discipline is easy to lose when the topic is so visually powerful. Frozen worlds, a dark frontier, hidden planets, ancient comets, a spacecraft flying beyond Pluto. These images tempt exaggeration, but exaggeration would make the belt smaller, not larger. It would turn a real frontier into a fantasy. The actual Kuiper Belt does not need to be inflated. It is already vast enough. Its reality is stranger than the false drama. It is strange that a region can contain millions of bodies and still be almost entirely empty. It is strange that a dwarf planet in deep cold can have active geology. It is strange that a small red object like Arrokoth can preserve a message from the era when planets were only beginning. It is strange that Neptune, a planet invisible to human eyes without instruments, can arrange the lives of objects billions of kilometers away. It is strange that our understanding of a major solar system structure began seriously only a few decades ago. And it is strange that all of this was hidden in plain sight behind a thin line on a poster. When we say the Kuiper Belt is beyond Neptune, the phrase sounds simple, almost geographic. But beyond Neptune is not a neighborhood just outside a city wall. It is a transformation of scale. The planets no longer define the architecture alone. Small bodies become the storytellers. Gravity writes in resonances. Time slows into centuries and millennia. Light weakens. Space opens. The familiar solar system gives way to an older and quieter one. The planets are the bright chapter. The Kuiper Belt is the footnote that turned out to contain the origin story. This is why the belt matters for Earth, even though it is so far away. Not because it threatens us directly in some simple way. Most Kuiper Belt objects are stable and remote. Their immediate influence on Earth is negligible. The importance is deeper. They explain how the system that produced Earth became arranged. The migration of the giant planets would have affected comet delivery, asteroid populations, impact histories, and the distribution of volatiles. The architecture of the outer solar system may have shaped the conditions under which the inner planets evolved. Earth is not isolated from the outer dark. It is part of the same history: water, organics, impactors, resonances, stability, bombardment, planetary migration. These are not separate stories. The Kuiper Belt helps connect them. It does not answer everything, but it provides constraints. It says the early solar system was more dynamic than the clean current arrangement suggests. It says the giant planets mattered not only where they ended up, but how they moved. It says small frozen bodies are not leftovers in a dismissive sense. They are witnesses. There is a quiet reversal here. The largest planets carved the system, but the smallest survivors preserved the evidence. Jupiter and Neptune moved worlds. Pluto and Arrokoth, remember. The future of Kuiper Belt science will likely come in layers. First, more surveys. A larger census will refine the statistical picture. How many objects are in each population? Where are the real edges? Which patterns survive after bias correction? Are the most distant orbits truly clustered? Are there hidden families waiting to be recognized? Second, better physical characterization. Colors, spectra, rotation periods, binary fractions, shapes inferred from occultations, thermal measurements. Each improves the transition from points of light to bodies with histories. Third, spacecraft. Nothing replaces proximity. A telescope can measure a dot. A flyby can reveal a world. An orbiter could reveal change, interior hints, seasonal cycles, surface processes, and geological context. But spacecraft to the Kuiper Belt are not easy dreams. They demand time, power, navigation, funding, and the willingness to wait through long silence. That waiting may be part of what makes them worthwhile. Civilizations reveal their values by what they are willing to study slowly. The Kuiper Belt cannot be consumed quickly. It cannot be reduced to one mission, one image, one discovery, or one dramatic headline. It is too large, too sparse, too varied. To understand it, humanity must build a science that thinks in decades and an imagination that survives distance. The classroom poster gave us a solar system that fits inside a glance. The real Kuiper Belt gives us a solar system that exceeds a lifetime. Picture it again, but differently now. Start at the sun, not as a symbol, but as a sphere of plasma, whose light takes 8 minutes to reach Earth. Move outward past the rocky planets, each separated by distances that would once have seemed enormous. Past Mars, the asteroid belt, Jupiter's empire of moons, Saturn's rings, Uranus tipped on its side, Neptune in its blue cold. Do not stop there. Let Neptune become a doorway. Beyond it, widen the darkness. Stretch the map until the belt is no longer a line, but a region. Fill it sparsely with frozen bodies, some tiny, some hundreds of kilometers wide, a few large enough to become dwarf planets. Tilt their orbits, lock some into resonance, scatter others outward. Make the whole structure puffy and uneven, shaped by a planet's migration and by billions of years of slow gravitational arithmetic. Then pull back farther. Add the scattered disk. Add Sedna's strange path. Add the inferred Oort cloud, not as a known photographed wall, but as a vast possible reservoir whose existence is written in the arrival of long-period comets. Let the solar system grow until the planets become the inner bright kernel of something much more extensive. Now, the old diagram looks almost innocent. It was not lying because it hated truth. It was lying because truth would not fit. But after a certain point, we have to stop blaming the page. The better picture is available now. We know enough to replace the old intuition. We know that the Kuiper Belt is not a narrow strip. We know that Pluto is not an isolated oddity. We know that Neptune's gravity sculpted distant orbits. We know that small, icy bodies preserve early solar system material. We know that the outer solar system is still incompletely mapped. We know that the border between known and unknown lies much farther out than school diagrams suggest. The question is whether we will allow that knowledge to change the emotional shape of the solar system. Because facts do not automatically become understanding. A person can know that the Kuiper Belt extends from around 30 to 50 astronomical units and still imagine it as a thin ring. A person can know that light takes hours to cross the outer planetary region and still feel that the planets sit close together. A person can know that the Oort cloud may extend toward interstellar distances and still think of the solar system as ending at Pluto. The old picture is sticky. It survives because it is simple. The real picture requires an act of mental expansion. Once you make that expansion, the solar system becomes more mysterious, not less. It is not merely the place where Earth orbits. It is a layered structure shaped by heat, frost, gravity, collision, migration, resonance, loss, and survival. The Kuiper Belt is one of its great borderlands, and like many borderlands, it reveals the history of both sides. It belongs to the Sun, but it points toward interstellar space. It contains bodies formed in the solar nebula, but its most distant cousins may be nudged by passing stars in the galaxy itself. It is local and cosmic at the same time. There is beauty in that position. The Kuiper Belt is not the center of the solar system, and it is not the end. It is a threshold. Thresholds are scientifically precious because they show transitions. Here the sun's warmth weakens into preservation. Planetary order gives way to debris architecture. The familiar planets give way to dwarf planets, contact binaries, resonant populations, and scattered orbits. Direct exploration gives way to inference. Known catalogs give way to vast, unseen numbers. The map becomes uncertain without becoming meaningless. That uncertainty is not a flaw in the story. It is the story. The Kuiper Belt teaches us that the solar system still contains unexplored geography, not in the romantic sense of blank spaces filled with monsters, but in the scientific sense of populations not yet counted, histories not yet reconstructed, and objects not yet visited. It teaches us that a small change in observation can create a large change in worldview. One faint moving point in 1992 transformed Pluto from a lonely planet into a member of a belt. One spacecraft in 2015 transformed Pluto from a point into a landscape. One flyby in 2019 transformed a small, cold, classical object into evidence about gentle planetesimal formation. What will the next faint point change? What will the next flyby correct? What pattern will emerge when tens of thousands of new objects are added to the map? These are not rhetorical decorations. They are active scientific questions. And behind all of them is the central correction this journey began with. The outer solar system is larger, emptier, older, and more structured than the picture in your head. The Kuiper Belt does not need to be made terrifying. Its scale is enough. Its silence is enough. Its patience is enough. It has circled the sun since before Earth had oceans, before life, before continents, before every human myth that tried to explain the lights in the sky. Its objects have watched the inner planets change from fire to crust to weather to biology. They have felt Neptune's distant pull, the faint light of the sun, the slow erosion of radiation, the occasional touch of impact. They have kept their cold archive while the rest of the solar system became dramatic. Perhaps that is why the belt feels so strange. It is not dramatic in the human way. It does not burn brightly. It does not crowd the sky. It does not announce itself. It simply remains wide and cold, waiting for a species from the warm inner system to notice that the edge was never the edge. The first time you learned the solar system, you were probably taught order. The next time you think of it, think in layers. The sun, the rocky worlds, the asteroid belt, the giant planets, Neptune's gate, the Kuiper Belt, broad and sparse, filled with icy bodies and dynamical memory, the scattered disk stretched outward by gravitational encounters, the Sedna-like frontier hinting at forces not yet fully understood, the Oort cloud inferred from comets, surrounding the whole system like a dim spherical possibility. Then, the passing stars. Then, the galaxy. This is a different solar system. Not because the objects changed, but because the frame widened. At the beginning, the Kuiper Belt looked like a little line beyond Neptune. By the end, it becomes a lesson in how much reality can be hidden by a correct but compressed drawing. It is a reminder that science often advances not by adding drama, but by restoring scale. The belt was always there. Pluto was always part of it. Arrokoth was always drifting in its ancient orbit. Neptune's resonances were always playing through the dark. The only thing that changed was our ability to see. And now that we have seen, the old map cannot be innocent anymore. The next time you imagine the solar system, do not let it collapse back into the neat row. Let there be distance. Let there be silence between worlds. Let Neptune be silence between worlds. Let Neptune stand not at the border, but at the entrance to a vast archive. Let Pluto become a known shore, not the end of the ocean. Let Arrokoth drift as a small red fossil of formation. Let the belt expand until it takes its true place. not a thin ring, not a leftover label, but a major province of the sun's domain. Out there, beyond the last planet, the solar system becomes cold enough to preserve its childhood. And that may be the deepest reason the Kuiper Belt matters. It is not just far away. It is old in a way the inner solar system can no longer be. Earth is alive and therefore restless. Mars has weathered and frozen. Venus has burned beneath its atmosphere. The moon has been battered. The giant planets have churned in storms. But in the Kuiper Belt, some bodies still keep the slow memory of the beginning. They are not unchanged in every detail, and we should never pretend they are perfect time capsules. But compared with the worlds closer to the sun, they are among the closest things we have to preserved pages from the first volume of our system's history. We are learning to read those pages one faint object at a time. A dot moves against the stars. An orbit is calculated. A color is measured. A resonance is recognized. A spacecraft is guided through billions of kilometers to arrive for a few hours beside a world no human eye could ever have seen unaided. From such small acts, the edge of the solar system becomes real. The Kuiper Belt was never a minor strip beyond Neptune. It was a vast, sparse, frozen record of how the solar system became itself. It shows that the planets are not the whole story, that leftovers can be evidence, that emptiness can be structured, and that a place too faint to see can still change the meaning of home. The old diagram gave you a solar system that ended neatly. The real one does not end so easily. It fades outward, through ice and resonance, through scattered worlds and inferred clouds, through distances so large that light itself takes hours, days, months, and then years to report back. And somewhere in that fading, in the cold beyond Neptune, the Kuiper Belt waits, not as a border, but as a beginning of the outer story. To understand why reading it is so hard, imagine designing a mission into the belt from the surface of Earth. The target is not merely far, it is also moving. Earth is moving around the sun. The spacecraft must first escape Earth, then the sun's inner gravity well, then cross the orbits of the giant planets, perhaps using one of them for a gravity assist, then arrive years later at a target that was a faint moving point when the mission was planned. The navigation problem is not like driving toward a mountain. It is like throwing a needle across an ocean at a grain of dust that will not be where it is now when the needle arrives. New Horizons did this once at Pluto, then again at Arrokoth, and that achievement can be easy to understate because the images have become familiar. A photograph makes a world feel close. But the photograph is the end of an almost impossible chain. Discovery, orbit determination, spacecraft design, launch energy, planetary alignment, course correction, navigation through the outer solar system, power management in deep cold, data compression, and then patience while signals crawl back to Earth at the speed of light across billions of kilometers. Even communication becomes a lesson in distance. A command sent to a spacecraft near Pluto takes hours to arrive. A reply takes hours to return. There is no real-time steering, no pilot with a joystick. The spacecraft must perform its encounter according to instructions sent long before the moment of closest approach. The human mind wants exploration to feel immediate. Immediate, like turning a camera towards something and looking. The Kuiper Belt refuses that intimacy. Every encounter is planned in the past, executed in silence, and understood later. That delay changes the emotional meaning of exploration. In the inner solar system, a rover on Mars is far away, but mission teams can work with a rhythm of days. In the Kuiper Belt, even the act of receiving data becomes a slow unfolding. The spacecraft passes its target in hours, but the full data set may take many months to transmit. A flyby becomes an event stretched across time. The world is visited quickly, but revealed gradually. This slowness is not a defect. It is part of the outer solar system's character. Everything there asks for long attention. Orbits last centuries. Seasonal cycles can take decades. Surface processes may operate on timescales far longer than written history. Even discovery is slow, because the objects move only slightly against the stars. The Kuiper Belt belongs to a universe where patience is not a virtue added to science. It is a requirement of the subject. That requirement also shapes what we know about composition. A distant point of light rarely tells you its full chemistry. Astronomers use reflected sunlight, infrared signatures, occultations, color measurements, thermal emission, and sometimes the behavior of moons to infer what an object is made of. A spectrum may reveal methane ice or water ice. A density estimate may imply a mixture of rock and ice. A color may suggest radiation-processed organics, but color alone does not give a complete recipe. The surface we see may not represent the interior. A thin coating can hide older material underneath. So when we call Kuiper Belt objects icy, we are making a broad and useful statement, not claiming that every body is a pure snowball. They are mixtures, rock and ice, volatiles and organics, surfaces altered by radiation, interiors that may have separated, compacted, warmed, or remained primitive depending on size and history. A dwarf planet and a small, cold, classical object can both live in the belt and still tell very different physical stories. Pluto tells one of the most complex stories. Its atmosphere is thin, but it matters. Nitrogen dominates it, with methane and carbon monoxide present in smaller amounts. Because Pluto's orbit is elliptical, sunlight changes over its long year, and the atmosphere responds. Volatile ices migrate across the surface. Frosts can sublime, move, and refreeze. The landscape is therefore not simply carved by impacts, it is shaped by a volatile cycle, a distant cousin of weather, operating under alien conditions. Sputnik Planitia, the great nitrogen ice basin, is especially important because it may have influenced Pluto's orientation. Its mass distribution, combined with subsurface and surface processes, has been studied as part of a larger question. How can a small world so far from the Sun remain geologically interesting? One possibility is that internal heat, antifreeze compounds, insulating layers, and the unusual behavior of nitrogen and water ice all help maintain activity longer than older, simple models expected. This does not mean Pluto is Earth-like. It means cold worlds can have their own geology, governed by materials that behave in unfamiliar ways. Karen adds another layer. It is large relative to Pluto, so large that the Pluto-Karen system is sometimes described as binary-like. The two worlds are tidally locked, each keeping the same face toward the other. Karen's surface shows canyons and tectonic features, hints that it too had an internal history. Its dark, reddish north polar region may be connected to material escaping from Pluto and being processed on Karen's surface. Even a moon in the Kuiper Belt becomes part of a chemical exchange between bodies. This is one of the reasons the word ice can mislead. On Earth, ice suggests stillness, fragility, a temporary winter skin. In the outer solar system, ice can be bedrock. Water, ice can form mountains. Nitrogen ice can flow. Methane frost can migrate. Carbon monoxide can participate in seasonal cycles. At temperatures far below anything familiar, substances change roles. What is gas here becomes solid there. What is a landscape material there would be an atmosphere or a vapor here. The Kuiper Belt is a chemistry lesson written under different temperatures. Arrokoth tells the opposite story, not of active complexity, but of preservation. Its low-speed merger suggests that at least some planetesimals formed through gentle assembly. That has consequences beyond one object. If small bodies in the outer solar nebula could form by the gravitational collapse of pebble clouds, or by other gentle concentration mechanisms, then early planet formation may have been less dominated by high-speed collisions than older simplified pictures suggested. Arrokoth does not settle every debate, but it provides a physical example. It shows that fragile shapes can survive for billions of years when the dynamical environment is calm enough. The cold classical population is therefore especially precious. These objects occupy a part of orbital space that appears less disturbed by Neptune's strongest scattering. Their colors, binaries, and low inclination suggest a population that may have formed near where it now resides. If true, they are not only leftover pieces of the solar system, they are local witnesses. Their existence constrains how far Neptune migrated, how violently, and how close it came to disrupting the region. But even here, caution is required. No population is labeled pristine because scientists know every detail of every object's past. Pristine means comparatively less disturbed, based on the best current dynamical and physical evidence. Over billions of years, collisions, radiation, weak perturbations, and internal changes can still occur. A preserved archive is not a perfect archive. It is a damaged archive that is still far better than most alternatives. The resonant populations are different kinds of archives. They preserve the movement of Neptune through the way objects became trapped. A resonance is not a cage with walls. It is a repeated timing relationship. Each orbit, Neptune gives a small gravitational tug at just the right phase, and over time that rhythm maintains the configuration. The mathematics can look abstract, but the result is physical. Entire populations remain protected because their timing avoids close encounters. Pluto's resonance is the famous case because it prevents close approaches to Neptune despite orbital crossing. But other resonances create other populations. Their relative numbers and orbital properties tell astronomers about the speed and smoothness of Neptune's migration. If Neptune moved too fast, some captures would be inefficient. If it moved too slowly, different structures would emerge. If it jumped suddenly because of encounters with another giant planet, the resonant architecture would carry a different signature. This is why the belt can be described as a detector of ancient planetary motion. We cannot watch Neptune migrate now. We cannot rewind the solar system. But the objects it captured, spared, excited, or scattered still carry the consequences of that migration. The belt is a gravitational seismograph whose needle stopped billions of years ago, leaving the trace in orbital space. Centaurs add another transitional piece. These are small bodies orbiting among the giant planets, often unstable over long timescales. Many are thought to come from the scattered disk or related reservoirs, temporarily entering the region of the giant planets before being ejected, colliding, or evolving into short-period comets. They remind us that the outer solar system is not a set of sealed boxes. Material can move between populations. A body can begin as a trans-Neptunian object, become a centaur, and later become a comet that approaches the inner solar system. Comets are therefore messengers from storage reservoirs. Short-period comets are often linked to the trans-Neptunian region and scattered disk. Long-period comets point toward the Oort cloud. When a comet grows a tail near the Sun, The dramatic sight in our sky may be the brief, visible phase of an object whose history was spent in cold darkness. The tail is not the comet's normal state. It is what happens when an ancient icy body is forced into the inner solar system and begins to lose material under sunlight. The Kuiper Belt is part of that broader comet story, but it is not simply a comet factory in the simple sense. Many objects there remain stable. Some are locked in resonances. Some are too large or too dynamically settled to become comets easily. The scattered disk is more dynamically active and is often considered an important source of Jupiter family comets. Again, the honest picture is more interesting than the simplified one. There is no single reservoir, no single path, no single destiny for icy bodies. The more we map these paths, the more the solar system looks like a living dynamical system rather than a static arrangement. Not living biologically, but active in the sense of gravitational exchange. Bodies are captured and released. Orbits diffuse. Resonances protect and destabilize. Passing stars and galactic tides matter in the farthest regions. The Sun's family is shaped not only by the Sun, but by the environment in which the Sun moves. That last point widens the story again. The Kuiper Belt is bound to the Sun, but the most distant outer reservoirs feel the galaxy. The Oort cloud, if its broad model is correct, exists where the Sun's grip becomes weak enough that external perturbations matter. A passing star does not need to collide with anything to change cometary orbits. The Milky Way's gravitational field can slowly alter distant paths. The solar system is not a sealed machine drifting through a neutral void. It is embedded in the galaxy. This does not mean the galaxy is constantly threatening Earth with sudden waves of comets in some dramatic, simple way. The dynamics are subtle, probabilistic, and spread over long times. Most perturbations do not produce visible consequences, but over geological time, rare events can matter. That is the outer solar system's style. Small gravitational changes, huge distances, long delays, occasional inner consequences. The Kuiper Belt also forces us to reconsider the meaning of the word edge. An edge can be a boundary where something stops, but many astronomical edges are not like walls. They are transitions in density, behavior, temperature, or dynamical control. The classical belt thins, the scattered disk stretches, detached objects appear. The Oort cloud is inferred. The heliosphere, the bubble carved by the solar wind, ends at a different kind of boundary entirely. The Sun's gravitational influence extends beyond the solar wind's dominance. Different definitions of the solar system produce different edges. This is why saying the solar system ends at Pluto was never merely outdated. It was conceptually wrong. It confused a famous object with a boundary. Pluto is not the edge. It is one body in a larger population. Even the Kuiper Belt is not the edge in every sense. It is the first great outer province. There is something almost philosophical in that correction, but it is grounded in mechanics. Our categories often arise from what is easiest to observe. The bright planets were known first, so they became the solar system in the human mind. Pluto was bright enough and large enough to become famous, so it became a boundary marker. The fainter belt objects remained unseen, so their absence from the story felt natural. Observational limits became conceptual limits. Science advances by noticing that those are not the same thing. A map of the solar system based only on what the naked eye can see ends at Saturn. A map based on 18th century telescopes reaches Uranus. A 19th century calculation and observation adds Neptune. A 20th century search adds Pluto. Late 20th century surveys reveal the Kuiper Belt. 21st century spacecraft reveal its surfaces. Future surveys may reveal hidden populations and decide the fate of Planet 9. The solar system has not been changing its size. Our doorway into it has been widening. That should make us careful about claiming completeness now. We know vastly more than our ancestors, but the Kuiper Belt itself is a recent warning against premature closure. The unknown is not always beyond other galaxies. Sometimes it begins just beyond the last planet on a poster. Even the term Kuiper Belt has history behind it. The existence of a trans-Neptunian population was considered by multiple scientists over the 20th century, and the naming reflects a complicated path of ideas rather than a single simple prediction. What matters for the documentary story is not who owns the name, but the fact that the belt moved from hypothesis to observation only when technology caught up. The object 1992 QB1 made the population undeniable. After that, each new discovery turned a lonely dot into a statistical family. Families change identity. Pluto became a dwarf planet because the family appeared. That is how scientific classification should work. Not as punishment, not as demotion for emotional reasons, but as an adjustment to a larger context. A whale is not a fish, because better biological context changed the category. Pluto is not a classical planet, because better solar system context changed the category. In both cases, the object becomes more meaningful, not less. To call Pluto a dwarf planet is not to reduce it. It is to place it where it belongs. Among the largest known members of the trans-Neptunian population, a complex world in a belt of ancient ice. The sadness some people felt came from losing a childhood list. The gain is a truer cosmic address, and that address matters because it is ours too. Earth is nowhere near the Kuiper Belt, but the story of Earth cannot be separated from the story of the outer disk. The same solar nebula produced both. The same giant planets shape the distribution of small bodies. The same early instabilities may have influenced impact rates and volatile delivery. The same sun binds the inner rocks and the outer ice. The solar system is one historical object. A planet is not only where it is now, it is also the history of the system that allowed it to remain there. That is why the Kuiper Belt belongs in a space science documentary not as an appendix, but as a central witness. If we want to understand why Earth exists in a stable orbit, why the giant planets are arranged as they are, why comets enter the inner system, why Pluto is complex, why small bodies preserve ancient material, and why planetary systems around other stars show belts and debris disks, then the Kuiper Belt is not optional. It is the cold memory of the architecture. When you next see an image of a debris disk around another star, remember that you are looking at a cousin of our own outer structures from too far away to resolve. A bright ring around Fomalhaut, a warped disk around Beta Pictoris, a cold belt around a nearby star. These are not just pretty astronomical images. They are reminders that planet formation leaves ruins everywhere. Planets are not born cleanly. They emerge from disks, disturb those disks, scatter remnants, and leave belts that later generations of astronomers can read. Our Kuiper Belt is the one such belt close enough to become detailed geology, not just distant glow. It is the bridge between exoplanetary debris disks and the hands-on study of small worlds. The more we learn, the more the word leftover changes. A leftover can be dismissed as waste. But in science, leftovers are often the evidence that matters most. A fossil is leftover bone. A meteorite is leftover rock. The cosmic microwave background is leftover light. The Kuiper Belt is leftover construction material, and because it was not built into a major planet, it can tell us how the building happened. The unused pieces sometimes explain the finished structure. That is the final reversal of the old diagram. The thin ring beyond Neptune was never a minor decoration. It was the part of the picture that knew the past. There is one more reason the Kuiper Belt deserves this slower attention. It teaches the difference between discovery and understanding. Discovery is the moment a faint point moves against the stars and receives a designation. Understanding begins later, when that point becomes part of a pattern. A single orbit can be strange. 10 strange orbits can be a coincidence. 1,000 carefully measured orbits can become a map of an ancient event. The belt is not understood object by object alone. It is understood statistically, dynamically, chemically, and historically. This is why future surveys are so important. A larger catalog does not merely add more names. It changes the questions we are allowed to ask. With enough objects, astronomers can test whether a clustering is real or only the footprint of where telescopes happen to look. They can separate color families. They can identify collision fragments. They can trace resonances with greater confidence. They can measure how the number of objects changes with size, which tells us how growth and collisions operated in the early outer disk. A faint dot by itself is a discovery. A population is a theory under construction. Occultations will also matter. When a distant Kuiper Belt object passes in front of a star, the star's light can briefly dim or disappear. The event may last only seconds, but it can reveal an object's size, shape, atmosphere, rings, or companion. Haumea's ring was discovered through this kind of stellar occultation. That is astonishing when you think about it. A small world, billions of kilometers away, passes over a distant star as seen from a narrow strip on Earth. And from that tiny shadow, astronomers infer structure no telescope could directly photograph. The outer solar system often reveals itself not by shining, but by blocking light. The belt also reminds us that scientific pictures have lifetimes. The first picture is not shameful because it is incomplete. It becomes a problem only when treated as final. The early planet list was useful. The early Pluto story was useful. The first rough Kuiper Belt maps were useful. But each had to yield when the data improved. That is not instability in science. That is science doing its work. A field that changes when evidence changes is not weak. It is alive. In that sense, the Kuiper Belt is a lesson in intellectual maturity. We can keep affection for the old images without obeying them. We can remember the childhood poster and still understand that it sacrificed scale. We can feel nostalgia for Pluto as the 9th planet and still accept that Pluto's real context is richer. We can say the solar system has 8 major planets and also say that the planets are not the whole solar system. We can hold a simple teaching map in one hand and a complex physical reality in the other. The deepest wonder is not that the simple map was wrong. It is that a more accurate map is more beautiful. The real outer solar system is not a messy correction that ruins the clean story. It is the story becoming worthy of the universe it describes. A thin ring becomes a vast archive. A demoted planet becomes a complex world. A cold, small body becomes a fossil of formation. A distant giant planet becomes a sculptor. Empty space becomes evidence of loss. Slow orbits become memory. And somewhere far beyond Neptune, the objects keep moving. Pluto continues along its tilted resonance. Arrokoth drifts in the cold classical belt. Eris crawls through its long, distant year. Sedna spends most of its orbit in a region so remote that Neptune can barely matter. Countless smaller bodies, unnamed and unseen, follow paths we have not measured. They do not care whether they are on a diagram. They are not waiting to be important. They are simply there, and our task is to make our picture large enough to include them. That is what the Kuiper Belt asks of us. Not fear, not fantasy, but enlargement. A larger map. A slower imagination. A willingness to let the solar system be stranger than the neat version and more coherent than the chaotic version. It is not a random dump of ice. It is not a crowded danger field. It is not a mere edge. It is a structured remnant, a gravitational record, a frozen population, a frontier close enough to begin exploring and distant enough to humble every claim of completion. When the solar system is drawn honestly, the planets no longer dominate the story alone. They become the bright islands in a much wider sea of time. The Kuiper Belt is one of the first dark waters beyond them. It is wide enough to swallow easy intuition, empty enough to expose the poverty of our diagrams, and old enough to remember the beginning. And that is why the belt changes the meaning of the word home. Home is not only the warm planet beneath our feet, it is also the architecture that made the planet possible, the remote reservoirs that shaped its history, and the ancient leftovers that prove our neighborhood was never simple. To know the Kuiper Belt is to realize that the solar system did not end where our childhood picture ended. It continued outward into cold, patient evidence, waiting for our instruments to grow quiet and precise enough to hear it. We have only just started reading it,